Hello and welcome to Note Quiz number 10, which is all about rational functions. The goal of this note quiz is to go through and identify all the key features of rational functions and then graph them using those key features. So before we get started on it, the first thing we want to do is talk about the basic form of a rational function. And it's really just a fraction made of two polynomials, a numerator and a denominator. We'll often call this the top and bottom of the fraction because it's a lot easier to use those short words than it is to use numerator and denominator over and over again. So let's go through and talk about some of the interesting features. For starters, the domain is usually going to be a restricted set. And when you find the domain of a rational function, you always focus your attention on the denominator or the bottom of the fraction. Remember, we can't divide by 0, so therefore any numbers that would force us to divide by 0, we have to exclude those from the domain. The next thing we do is we factor down the polynomials in the numerator and denominator completely. So write it in a totally factored form if possible. From there, what you can do is notice that the x-intercepts are going to be the zeros of the numerator. The y-intercept we just get from substituting in 0 into the function and simplifying. And then to find our next features, they're called asymptotes. And to find asymptotes, what you do is you take your factored form and you look at your denominator. If anything cancels from the denominator, that is not going to make a vertical asymptote. Instead, it's going to make a hole in the graph. And the vertical asymptotes are going to be lines that are vertical that are going to break up the graph into pieces, and it's going to be the number that would force you to divide by 0. And so vertical asymptotes are vertical lines going up and down that divide the graph into pieces. And then we have what are called horizontal asymptotes. And those come from looking at what value the function approaches as you go to the far right of the graph towards positive infinity, and what happens when you go to the far left of the graph towards negative infinity. Is the graph settling in on a number? Is it growing forever? Is it going to 0? Or so on. So horizontal asymptotes will describe that behavior. And it's also possible to have what's called a slant asymptote, where it's a diagonal line that the function approaches as you go to the far left or far right. And so we'll talk more about finding those features in a few minutes. The other thing you'll see is going to be what's called crossover points. Crossover points are where the function crosses any horizontal asymptote. So we find the domain first, try to find the intercepts if they exist. We then look for vertical asymptotes, holes in the graph, horizontal asymptotes, or possibly slant asymptotes. Then we put all of that together onto a graph and then sketch the rational function. At that point, you may also need to plot a few points because we want to have a graph that is highly respectable, and we can actually use it for further work, especially when you get into take classes like pre-calc or calculus. So we want to draw a fairly accurate graph that we can rely on, but don't stress too much about having the whole thing be perfectly passing through all the points. Again, we want to make sure the behavior is captured more than anything else. All right, so now let's dive into some problems. For our first problem, we're going to start nice and slow and just focus on domain. So they want us to find the domain for this rational function. And again, that always comes from your denominator. So we're going to take our x squared minus x minus 12 and set it equal to 0. Most of the time, these are going to factor down very nicely. This factors as x minus 4 and x plus 3 equals 0. So x is either equal to 4 or x is equal to negative 3. Now these are the two bad numbers that you want to exclude from your domain. So I find it very helpful to put them both on a number line and draw something like a red X through them to remember that they are bad numbers. And then everything else on the left side of negative 3, everything between negative 3 and 4, and then everything right of 4, those are the good numbers. So we want to use interval notation to represent this. We're going to start at negative infinity up to negative 3, union negative 3 to 4 to capture the middle, and then finally 4 to infinity. think of it as a number line with two holes punched out, one at -3 and one at 4. And again, that's the set of all the numbers that we can use in our function. So that right there is how we find domain. You will notice that we did not spend any time whatsoever looking at the numerator of the fraction. It plays no role in finding the domain. It's all about that possibility of dividing by 0 that we have to be careful for with rational functions. All right, so now let's shift gears and kind of talk about the brand new feature, which are asymptotes. Asymptotes are going to be either a vertical line that divides the graph into two parts, and every once in a while we'll see horizontal lines that are going to divide the graph, but these have a very different thing going on. You can never, ever, ever cross a vertical asymptote. And again, that's that line going up and down through here. However, it is possible for some rational functions to cross their horizontal asymptote here. This simple example here doesn't do that, but we will see that in other problems coming up. So the idea is for a horizontal asymptote, you're looking at what happens to the far left or the far right of the graph. And you'll notice that as I go towards -infinity, I'm going to the far left. And what that means is what's happening to my function values, my outputs. And you notice that they're going up closer and closer to 1, but they never reach 1 in this case. So as x goes to the far, far left, my function approaches 1. We'll do these out of order and talk about letter D. As x goes to the far, far right, you will also notice that it approaches a y value of 1. What's different is you're approaching 1 from the underside on the left, and you're decreasing down to 1 from above on the right. But we don't care about that. You will later on. But right now, in algebra, we just care about the fact that the function approaches 1 as you go to the far left and you go to the far right. Now let's talk about 3. Again, x equals 3 has a vertical dashed red line going through it. And you want to look at what happens as you approach 3 from the left. So what's happening in this direction? And you'll notice that you're riding this blue curve down forever. So that direction is negative because you're going down to negative y values, and it's forever, so therefore it's going to be -infinity. If you now look at the right side of the graph, you will notice that as you approach 3 from the right, those values are all getting bigger in the positive direction, going up this way. So that's going to be in the positive infinity direction. And you could just write regular infinity without a sign, and it captures the same idea. But at a vertical asymptote, you will always go towards infinity. Horizontal asymptotes will always have you approaching a number, and that's a very important contrast here. So keep that in mind as you look at rational functions. Vertical things are infinite. Horizontal things will be numbers if they exist at all. All right, so let's move on to other questions about this graph. You will notice that this function is always going down. As I move from left to right and read it, the blue curve is going down. And then when I start on the other side of 3, the blue curve is still going down. So this thing is always decreasing. And we're going to say that it's going to start at -infinity up to 3, and then from 3 to infinity. We don't say it's decreasing at 3 because 3 is not a point on the graph. You'll notice that it's never getting bigger. The blues are always going down, so it's never, in this case, increasing. Now, next up, let's talk about the domain and the range. You could figure out pretty quickly that the domain is going to be the same thing as the decreasing answer because there's an x value for every single point except for 3. So my domain is going to look exactly the same. -infinity to 3, union 3 to infinity. We now look at the range. The range is a little different, and we haven't seen much of this yet, but the idea is that it goes down forever and stops short of 1 and never reaches 1, and then it starts above 1 and goes up forever. So it's going to be from -infinity up to 1, and then from 1 to infinity. And for this function, it is impossible to get an answer of 1 for the function. No matter what you plug in or evaluate, you'll never get a 1 for an output. You'll get as close as you want to 1, but you never get a 1. So now we can just read our graph to state our asymptotes. A very important thing to keep in mind with asymptotes is vertical asymptotes always have an x equals because they're vertical lines. So it's x equals 3. A 3 doesn't cut it because we don't know where the 3 is. Is it up, down? Who knows? The horizontal asymptotes, they always have a y equals, and in this case, that is y equals 1, because that's the number that we approach from the left and the right as we go to the far parts of the graph. So again, vertical asymptotes must always have an x equals, horizontal asymptotes must always have a y equals. It is absolutely necessary. All right, so now let's move on to how to find these vertical asymptotes. And to find these, it's actually kind of easy if we can just go through and factor very carefully. So off to the side, not in the middle of my problem, I'm going to take my denominator and I'm going to factor it. I'm going to take that 5x squared minus 16x plus 3 and factor it. And we'll use the grouping method or the AC method. I'm going to take the 5 and the 3 to get 15. And the pair of numbers that multiply to make 15 and add up to negative 16 are negative 1 and negative 15. So that's really a 5x squared minus a 1x minus a 15x plus 3. Now I can use grouping the first two and the second two, being careful with signs. In the first, I take out an x. And let's see here. That's not right. Something is wrong. Let's see here. No, that's going to be... I can take out a 3. All right, so let's just kind of keep going. Let's not be too careful about it. Let's do 5x minus 1. And back there, yeah, I can take out a 3. And I get a 5x minus 1. So taking out a 5x minus 1 leaves me with an x in the first and a minus 3 in the second. So again, all I'm going to do now is rewrite my g of x. It is x minus 3 divided by 5x minus 1 and x minus 3. All right, now this is where it gets very important to be very, very careful. If you have a factor that cancels out with your numerator and denominator, you can cancel it out. And that is going to tell you that you have a hole at that number, x equals 3. And holes are basically just an empty missing spot on your graph. However, when you look at the leftover part that doesn't cancel, this 5x minus 1 equals 0 is going to give you a vertical asymptote. So x equals 1/5 is the location of the vertical asymptote in this case. And again, the x minus 3 tells us there's a hole in the graph, but a hole in the graph is not the same thing as one of those vertical lines going up and down that breaks it apart. And again, if you go on to take calculus or pre-calculus, you'll talk a lot more about holes, which are often called removable discontinuities. But again, don't worry about that now. All right, next thing to talk about here is going to be horizontal asymptotes. And at the college algebra and the pre-calculus level, we look at comparing the degrees. So for this first one here, you will notice that they both have a highest power of x squared. So in writing this out with a little bit of explanation, the degree of, we'll say, the top is 2, and that's the same thing as the degree of the bottom of the fraction. And because the degrees are the same, we take y is equal to the ratio of the leading coefficients. So upstairs, the leading coefficient on x squared is -5. And down below, the leading coefficient on 1x squared is 1. So my horizontal asymptote is y is equal to a -5. And again, what that means is that the far right of the graph and the far left of the graph approach -5 as you go on in both those directions. You'll notice for the next problem that it's called top heavy. The degree of the top is 3, and that is bigger than the degree of the bottom, which is 1, because that's just x to the first down there. So we call this thing top heavy. And there is no horizontal asymptote. There's just none whatsoever, which means there's no horizontal line that you approach as you go to the right or left. And what's really happening here in a more abstract sense is the fact that the numerator grows faster and outpaces your denominator. So it doesn't settle in or converge to a number. It just grows forever going up to the upper right corner. So no horizontal asymptotes here. For this last one, you will notice that the bottom is larger. It's an x squared, second degree, and the top is linear or first degree. So in this case, the degree of the top, which again is 1, is less than 2, which is your degree of the bottom of the fraction. So this is sometimes called bottom heavy. And in this case, the answer is always y equals 0. And what that means is that as you go to the far right, this goes to 0, the x-axis. And as you go to the far left, it goes to 0, which is the x-axis. And again, the idea in an abstract sense, the denominator outgrows the numerator and pulls the overall fraction down to 0. So that's the best way to think about these horizontal asymptotes. And that's the 3 cases. Either the powers are equal and balanced, either the top is too big and it's a no situation, or the bottom is too big and it's the 0 situation. And always try to understand the difference between none versus 0. All right, so next up, we're going to talk about what are called slant asymptotes. And so for a slant asymptote, it's always going to result from the case where you have a function that has a top that outgrows the bottom. And you'll notice that the degree of the top is 2, the degree of the bottom is 1. So to find what's called the slant asymptote, you divide. You're going to take your x plus 3 and use long division to divide it into x squared plus 7x plus 2. And we saw in the last note quiz that you just divide and get a remainder. So x times what makes x squared? Well, that's x. Then you multiply, you get an x squared plus 3x. And then you change the signs and add them up, so those both become minuses. Combine like terms, and you get a 4x coming down. And then we bring down the plus 2 that's over there. And we repeat the process. X times what makes 4x? It's 4. So we put plus 4 up here. Multiply it out. We get a 4x. And we get a 12. We once again subtract. Remember, you do that by changing the signs and adding them up. So that's a minus, and that's a minus. And 2 minus 12 is going to give us a negative 10. So the slant asymptote is y equals x plus 4. And what that means is as you graph to the far left and the far right, it approaches the line x equals 4. In a more abstract sense, the idea is that x squared plus 7x plus 2 over x minus 3 is equal to the quotient x plus 4 plus our remainder, negative 10, over x plus 3. And for very large values of x, this becomes a smaller and smaller fraction that disappears because the 10 is staying the same and the x is getting bigger. So what's left over is this x plus 4. That's what gives you the graph on the far extreme parts. So again, slant asymptotes are found by doing long division, and your quotient gives you the formula for the slant asymptote with the y equals. All right, so now for the next problem, we're going to go through and identify asymptotes. And you'll notice they want us to get the vertical, and they want us to get either the horizontal or the slant. Keep in mind here again that it's impossible to have both a horizontal and a slant, because technically the slant asymptote comes from the horizontal not existing. All right, so again, the first thing to do when you're trying to find asymptotes is to factor completely. So when I factor this completely, you'll notice I can first take out a 2 upstairs. Is with x squared minus 3x minus 4. I'll just write the bottom down as is for now. And then I can factor this a little further. Taking out the 2, I'm left with x minus 4 upstairs and x plus 1. Down below, I've got x plus 1 and x minus 1 from the difference of squares. And then we said before that when you have everything completely factored, if something cancels out, that does not give you a vertical asymptote. So no VA from the cancellation. However, the part that doesn't cancel down below, that gives you your vertical asymptote. So x minus 1 equals 0, or x equals 1 is my vertical asymptote. Now, let's look at the degrees and the powers. You will notice that they are both second powers. So the degree of the top is equal to the degree of the bottom, which is, by the way, 2. So we take the ratio of leading coefficients. So y is equal to the number in front of x squared, 2, divided by the number in front of x squared down below, which is 1. So it's y equals 2. And again, we circle, that's a horizontal asymptote. All right, so that's the vertical and horizontal for that equation there, or that function there. All right, so the next problem is going to have us going through and doing a much more detailed analysis and having us actually sketch a graph. So let's do that next. So for the next problem, we give us a simple rational function, which is 2x minus 8 divided by x plus 3. First thing you want to do is find your domain. Remember that comes from your denominator, so we're going to take the x plus 3, set that equal to 0, so x is negative 3. Remember again, negative 3 is your bad number. You do not want to include it, and everything else is good. So your domain is going to be from negative infinity to negative 3, union negative 3 to infinity. All right, next up, we find x-intercepts. Remember, x-intercepts come from setting your function equal to 0. So that's a 2x minus 8 over x plus 3 equaling 0. You will notice in this calculation that if you multiply both sides by x plus 3, it disappears from the equation solving process. And you just get 2x minus 8 equals 0, or 2x equals 8, or x equals 4. So my x-intercept is 4, 0. Now let's find the y-intercept. The y-intercept, remember that comes from taking your x number and setting it equal to 0. So in this case, it's h of 0. If I plug a 0 into the top, I get negative 8. A 0 in the bottom makes 3. So the y-intercept is 0, negative 8 thirds. All right, so we found our intercepts. Now let's move on to the asymptotes. For the asymptotes, we're going to first look at vertical. For vertical, remember we write it in a factored form. So that's h of x, and if I factor the top, I can take out a 2, and I'm left with x minus 4. Down below, I've got x plus 3. Nothing cancels, so that x plus 3 sitting down below tells me that x plus 3 equals 0 is my vertical asymptote. So x is negative 3. You will notice that that's the same thing as the exclusion in our domain. All right, now let's take a look at horizontal asymptotes. We look at degrees. They're the same. So the degree of the top equals the degree of the bottom, because 1 equals 1. They're both first power. So my leading coefficients is y is equal to 2 over 1, or y is just 2. Again, that was a horizontal because the powers are the same. A new thing to talk about here is the crossover point. The crossover point is where the function matches the value of the horizontal asymptote. So we set our h of x equal to 2. So we get a 2x minus 8 over x plus 3 equals 2. If we cross multiply, we get 2x minus 8 equals 2 times x plus 3. And that's going to give us 2x minus 8 equals 2x plus 6. If I cancel out my 2x's, I get negative 8 equals 6, which we know is never going to happen. So that means there are no crossover points for this function. It is not going to cross the horizontal asymptote. All right, now let's piece everything together and draw the best graph that we can. So when we graph this thing, you always start with your asymptotes first. So we saw there's a vertical asymptote at negative 3. So I draw a dotted line above and below that cuts through, and we label it. It's good practice to do that. We also have a horizontal asymptote, which was y equals 2. So we draw that in here as well. And we label it. We also saw that we had a x-intercept of 4, 0, which is right there. And we had a y-intercept that was negative 8/3. And negative 8/3 is negative 2 2/3. So that's right in between negative 2 and negative 3 here. Now remember, you cannot cross the vertical asymptotes. And in this particular problem, you also can't cross the horizontal, which means that your graph on this side must look like this because you are approaching the asymptotes. On the other side, you really can't tell if it's going to be above or below the horizontal unless you check either the sign of your answer, positives and negatives, or just better yet, plot a point. Calculate h of, say, negative 4 and see what it gives you. If I stick a negative 4 in this, I'm going to have 2 times negative 4 minus 4 over negative 4 plus 3, which is 2 times negative 8 divided by negative 1. That's going to be a 16, which is a positive number. That means at negative 4, I am way up here at negative 16, which means that my graph must look like this. It's the only way I'm going to pass through a 16 is to be going up in that direction. And again, if I would have got a negative number, it'd be below the horizontal asymptote instead. All right, so there's our complete graph for this problem here. And again, you're always welcome to go to a graphing calculator or Desmos and take a look at your answer and see if it matches. Those are a good way to check them. All right, so let's do this next problem, and it's going to get a little choppy and a little noisy. There's an idiot going up and down the road on a little motorbike, so my apologies now for the external sounds that may make this a little more harder to follow. But anyways, let's start off with the domain. Again, it always starts off with our denominator, which we know is x squared minus 2x minus 3 equals 0. And we factor as x minus 3 and x plus 1 equals 0. So x equals 3 and x is negative 1. Remember again, those are the bad numbers. We don't want to have them in our final answer. So I like to draw a number line and stick them on there. Stick on the negative 1, stick on the 3, and again, use some kind of symbol to represent that they are bad. I'll use red X's. So my domain is going to be left of negative 1, in between negative 1 and 3, or right of 3. In interval notation, that is negative infinity to negative 1, union negative 1 to 3, union 3 to infinity. All right, next up, we'll go through and find x and y intercepts. So let's first get the y-intercept. Remember that is setting the x equal to 0. In this case, it's finding c of 0. And we get 3 times 0 over basically negative 3. That's going to work out to be 0. So my y-intercept has an x value of 0 and a y value of 0. Again, the denominator does not play a role in getting our x-intercepts. Why did I say y-intercept? Okay, so it was 0. So I put that in the right spot. Sorry, getting a little distracted by the outside noise there. So my apologies. Now let's get the x-intercept. That's where you set the function, whatever it may be. In this case, it's c of x equal to 0. If I've got a 3x over x squared minus 2x minus 3, and that's equal to 0, the only way that fraction is going to equal 0 is if my numerator is 0. Again, I could multiply by the LCD and get rid of it, but in any case, it's going to be when 3x is 0, which makes x equal to 0. So the x-intercept is the same as the y-intercept. It is the point 0, 0. That will happen sometimes. All right, now let's move on to our asymptotes. Let's first return to our function and write it in a factored form. It's a 3x, and we factored already. That's x minus 3 and x plus 1. You will notice nothing cancels. And because nothing cancels, both of these are going to give us the location of a vertical asymptote. So the first one comes from x minus 3 equals 0, which happens at x equals 3. The second one comes from x plus 1 equals 0, so x is negative 1. Remember, when you state your answer, you gotta put the x equals in front of those. It should be no coincidence at all that the two vertical asymptotes are also the places where you punched out your domain, your negative 1 and your 3. All right, now let's move on to horizontal. For horizontal, again, we compare degrees. And you notice that the degree of the top is smaller than the degree of the bottom. The degree of the top is 1. Not a 2, I don't know where that came from. 1 is less than 2. So that means that y equals 0 must be the equation for this horizontal asymptote. It is bottom heavy. Crossover points come from setting the function equal to the value of the horizontal asymptote. So that is going to be 3x over x squared minus 2x minus 3 equals 0. And we just solved that a few minutes ago when we found our x-intercepts. That implies that x equals 0. So the crossover point is also 0, 0. So we've got an x-intercept and a y-intercept and a crossover point all being the origin. That's simple to remember, but it's also not a lot of information for graphing, which is unfortunate. All right, so now let's piece it all together and draw our graph. Remember, we start with vertical asymptotes first. So I'm going to draw a dashed vertical line through x equals 3, and another one through x equals -1. All right, so again, that is x equals -1, x equals 3. My horizontal we found was y equals 0, which is basically your x-axis. I'm going to draw it a little above there for so we can see it. All right, so we already saw that we have a crossover point at the origin. So I'm going to put a large dot right there at 0, 0. And now we have to figure out if we're above or below. So it's really important at this point to maybe think about what our function was again. It was c of x is 3x divided by x minus 3 and x plus 1. So now we can just pick some points. You should notice that if you were to plug in a 4 and calculate c of 4, you'd get a 12 upstairs, and down below you get a 1 times a 5, which is just 12/5, which is 2 and 2/5. So again, when x is 4, you're a little above a 2. That puts our graph up here above. All right, next up, we have another point to calculate. Let's calculate c of 1 right next to the crossover point. C of 1 gives me a 3 upstairs, gives me a -2 times a 2. That is -3/4. So when x is 1, I'm at -3/4. So it tells me that the graph must look something like this here. Remember again, these are smooth, so don't draw sharp, jagged things. And then finally, I need to find out what's happening on the other side, on the left. Let's calculate c of -2. C of -2 is going to be 3 times -2 divided by -2 minus 3 times -2 plus 1. So that's a -6 with a -5 and a -1. That makes -6/5, which is a little past -1. So that's going to be down here, right around that point. And again, remember I can't cross my verticals, and we don't cross the horizontal either because we found the one crossover point already. So my graph is going to look something like this right here, where I come up and then back over like so. All right, so that is the graph of that rational function. And again, you could go to Desmos or a graphing calculator and verify that. You can also plot more points if you wanted a more accurate picture, but this is actually pretty good. All right, so now let's move on to our very last problem in this note quiz. And it's going to be basically the same thing all over again. So we're going to first focus on the domain. And again, we're going to take our 2x squared minus 18 and set it equal to 0. And that's 2 times x squared minus 9 equals 0. So that's 2 times x plus 3 and x minus 3, because that's a difference of squares. So -3 and +3 are the two bad numbers. Once again, draw a number line, stick your -3 on it, stick your 3 on it, put some red x's over the bad numbers, and just fill in what you want. So my domain is going to be, make some more room here, it's going to be -infinity to -3, union -3 to 3, union 3 to infinity. All right, now I'll find x-intercepts and y-intercepts. Remember again that the x-intercepts are going to come from setting the function c of x equal to 0, which in this case is taking our numerator and setting it equal to 0. Taking out a greatest common factor of 6, I'm left with x squared minus 2x minus 8 equals 0. And I can factor that as x minus 4 and x plus 2 equals 0. So I'm going to get a value of, let's see here, x equals 4 and x equals negative 2. I'm out of room. So my x-intercepts are 4, 0 and negative 2, 0. Remember the y-intercept? Well, that just comes from setting the x equal to 0. And when you calculate c of 0, all the x terms are going to vanish, and you're left with a negative 48 upstairs and a negative 18 down below. You can reduce that down by 6 to get 8/3. So 0, 8/3 is your y-intercept. And these are actually kind of nice things to have here because we have some extra points for plotting, which is going to be wonderful. All right, now let's go on to get our vertical asymptotes. And remember that has us going back and writing the function in a completely factored form. The numerator we saw can be factored as 6 times x minus 4 and x plus 2. My denominator can be factored as 2 times x plus 3 and x minus 3. You will notice that nothing cancels. So both of those are going to give me a vertical asymptote. I've got x equals negative 3 and x equals positive 3. And again, hate to sound too redundant here, but remember that the exclusions in your domain are going to match those, including any holes you may possibly have, which we don't have. Next up, let's do the horizontal. That comes from comparing degrees. The degree of the top, you notice, equals the degree of the bottom. They're both second degree polynomials. So I'm going to take the ratio, which is y is equal to the coefficient on the top is 6, coefficient on the bottom is 2, and of course that's 3. So y equals 3 is my horizontal asymptote. There are no slants. Now let's get our crossover point. Crossover point takes the function and setting it equal to the number in the horizontal asymptote. And I wish there was more room here for it, but there isn't. We'll just make the best of it. That is 6x squared minus 12x minus 48 over 2x squared minus 18 equals 3. If I cross multiply, I get 6x squared minus 12x minus 48 is equal to 3 times 2x squared minus 18. If I now compare this, I get a 6x squared minus 54. In this calculation, you will notice that my 6x squareds cancel out, and I can add a 48 onto both sides. That takes me to negative 12x is equal to negative 6 dividing by negative 12. I get x equals 1/2. So the x number is 1/2. There is no need to calculate the y number because we just got done setting it equal to 3. So 3 must be the y number. All right, now let's put it all together for our supergraph. So once again, we've got vertical asymptotes at 3, and negative 3. And coincidentally for this problem, a horizontal asymptote at 3 as well. So a lot of 3's in this problem. All right, and again, it's always a good habit to label them. So this is x equals negative 3, this is x equals positive 3, and that's y equals positive 3. All right, now we can put on our other features. So we saw that we had a x-intercept here at 4, 0. And we had another one at negative 2, 0. And we also had a y-intercept of 8/3, which is 2 2/3. All right, so we have the 4 points that we found so far. And now the next thing we want to do is we want to go in and we want to, actually we can put our crossover point in there too. So before I forget that was 1/2, comma 3. So, and again, that's right on our horizontal asymptote. So that is right here. So now we can start drawing our graph. Remember again, you cannot cross the vertical asymptote. So we're going to have a graph that is going to start here and go down like so. Next up, in the middle, we do cross over the horizontal at the 1/2 point. So my graph should look something like this here. Remember, you are approaching those vertical asymptotes. And then the last thing to be done is to figure out what's happening on the far left. So let's just calculate c of negative 4. When you calculate c of negative 4, you're going to have 6 times negative 8 times negative 2 divided by 2 times negative 1 times a negative 7. That's going to simplify down to 48 over 7, which is just short of the number 7. So that's going to put us right there. Remember again, you can't cross the vertical asymptote, and we can't cross the y, not the y, let's call it the horizontal asymptote, that's what I meant to say. You can't cross that either because we already found the one crossover point. So the last part of the graph must look like this. And so that is a complete graph of our rational function. Again, if you wanted to get a little bit more accurate, you could, of course, plot points. And remember, when you're drawing these, you actually don't touch these asymptotes. You get very, very close to them. So if you're going to be a little OCD about things, remember you could actually draw them a little nicer and draw them where you're coming up and going over, and so. Just remember, you must always pass the vertical line test because you're graphing a function. So make sure that whatever you graph, it doesn't double back on itself and fail the vertical line test. So try to take some time and some care when you're graphing these, and you'll get really nice pictures. And that wraps up note quiz number 10 on rational functions. So again, before you do any problems, you should always start off with the beginning checklist and go through and find all the features and then draw a nice accurate graph. All right, so, and that's the end of the video, but there are going to be about 30 seconds of goofy sounds, such as dogs eating dog food and walking around on a hardwood floor. So my apologies for the noises in the background, but that's what happens when you have editing issues with videos. So again, my apologies for the weird silence for the next couple seconds before we stop it.